I'm going to be talking to Professor Radisav Vidic, who is the chair of the Department of Civil and Environmental Engineering at the University of Pittsburgh, about a new method for reducing the environmental impact of drilling and fracking for oil and gas by cleaning the produced water. That is a big issue. Wastewater is often re-injected into wells and has caused, in Oklahoma, for instance, has caused earthquakes, quite a few earthquakes, and there's always concern about the seepage into groundwater. So big issue. Welcome to the interview.
Good to be here.
Can you give us a description, please, of how this technology works?
Okay, so membrane distillation technology is based on using a hydrophobic membrane, meaning the membrane doesn't like water, and using it as a barrier between dirty water and clean water. So when you put the dirty water on one side of that membrane, it won't go through because it's hydrophobic. The water won't go through. But if you heat the feed side, the dirty water, if you heat it up, then the water vapor can distill to the other side of the hydrophobic membrane. Kind of like a distillation, classical distillation. You heat up the water, only the water evaporates, all the salts and everything stays behind. The advantage here is in the membrane distillation, you have enormous area available for the mass transfer of water vapor from the dirty side of the water to the clean side of the water. You're basically transferring just the water vapor onto the clean side.
So help me visualize how this works. Do you put the membrane unit, the filtration unit, does it go on a battery lease, or do you have to pump it to a central location to do the cleaning?
Well, you have to have a central plant that's equipped with membrane distillation modules, kind of like a reverse osmosis. It's a spiral wound membrane module, and you're pushing water through this spiral wound membrane module. So you have a lot of surface area available for mass transfer. Now, these membrane distillation units can be made mobile. You can move it from site to site to do the cleanup job, or you can build one big centralized facility and bring all the water to it to clean it.
And what about the material that's taken out of the produced water, the salts and the, whatever other toxic materials it removes?
So the membrane distillation is not going to give you a zero liquid discharge. Depending on what's the salinity of the water that you're treating, you can recover 40, 50, 60%, 70% of the water as a clean distillate. You will still end up having some reject stream that's a concentrate, and so all the salts and everything is going to stay in that stream, but the volume of it is going to be smaller, and you can easily handle that, much easier to handle that. You don't have to pump into disposal wells as fast and as a high pressure to be able to get rid of it. And at the same time, you recover some clean water that can be used for agriculture, for livestock, for industrial uses, and so forth.
I've seen this debate around how much you clean the water in other instances, for instance, the Alberta oil sands, when they're talking about cleaning tailings ponds. The question is, how is it drinking water? Is it industrial to an industrial standard? What's the standard here?
Well, the standard here is going to depend on what kind of volatile compounds do you have in the feed. So, for example, if you have some volatile organics in the feed side that can be evaporated at this low temperature, we're talking about 60 or 70 degrees Celsius, they will come across with the water vapor. You can't do anything about it. Some ammonia may come across. So I wouldn't call it a drinking water standards for two reasons. One is nobody would drink the water that came out of this oil and gas industry, regardless of how clean it is. Even if it's a perfectly clean, nobody would use it for drinking purposes. So then you can apply polishing steps later on if you want to clean it up for groundwater recharge, for example. That would be one other idea. The problem with the current approach with oil and gas industry is that the cheapest method to get rid of this water is to just dispose it into a class 2 injection wells. Just pump it deep into the subsurface. That is the cheapest option, but it's also the worst because all of that water is permanently lost from the hydrologic cycle. You may be taking the surface water to frack the well, you may be taking the groundwater to frack the well, and once you dispose it into deep wells, then it's gone. You're not going to be able to use it ever again. So the idea is to reduce the water footprint of this industry, to reduce the environmental footprint of this industry by recovering some clean water that can be used for other industrial agricultural uses.
And transporting that can be very expensive now. In places like Texas and Oklahoma, they do it with pipelines. But I gather you're in Pittsburgh, so in Pennsylvania, they actually have to truck the water to Ohio?
Yeah. That is the biggest cost of managing this water. Right now, over 90% of water in Pennsylvania, of the produced water in Pennsylvania, is reused for hydraulically fracturing the next well. And that works only as long as you have another well to frack. But every well field at some point becomes a net producer of water. You initially need a lot of water to frack the wells, and you can reuse the produced water to frack the subsequent wells. But at some point, your water demand for operation is going to be less than the amount of water that you're producing. At that point, somebody's going to have to pay the piper and do something with this water. Since we do not have disposal wells in Pennsylvania, in some instances, they're trucking water a couple hundred miles, and that is not only expensive, but think about the CO2 emissions, particulate emissions with diesel engines, and all these other environmental implications of transporting this water the long distance. So if you can reduce the volume of water that you have to truck to Ohio or some disposal wells, then you would save a lot of money by just simply reducing the volume of water that you have to truck, and at the same time, you are recovering some water that may be useful to somebody in the region.
Final question, Professor Vidic. What is your new method economical? Like, is it actually a cost saver for the industry?
The critical thing with any thermal technology, you have to heat the water. So the most expensive part of it is heating the feed to 60 or 70 degrees. Now, that is the costliest proposition here of treating the water with membrane distillation. So you can imagine that if I had to pay for the heat to generate the steam, or if I have to burn natural gas to generate the heat, that would be quite expensive, although it would still save them money by reducing the volume of water that they have to truck, because the transportation costs are phenomenal. But the trick is to actually find ways to use some waste heat. This is the beauty of this technology, because you do not have to use a high quality heat, because you only have to heat this water to 60 or 70 or 80 degrees Celsius. And so if you can find the waste heat, and in oil and gas industry, there's plenty of waste heat. For example, compressor stations that are used to move the natural gas from the point of production to the point of use, they operate on the compressors that basically burn a portion of the natural gas in order to run the turbine. Now, when they burn the natural gas, the exhaust gas that comes out of burning the natural gas, it's quite hot. And we found out that there is enormous amount of waste heat generated by the compressor stations, and that waste heat would be sufficient to treat the water in Pennsylvania to, from 100,000 milligram per liter to 300,000 milligram per liter to saturation, recover somewhere in the order of maybe 50, 60% of water. And in that case, the cost of membrane distillation is about the same as the cost of the reverse osmosis seawater desalination process. So then it becomes economical if you have a waste heat to operate a plant. But you would still save money even if you have to pay for the heat, because the cost of transportation is phenomenal. Even if you have to pay for the heat, it's still cheaper to recover some clean water, leave it on the site, or use it for something else and transport half the volume to Ohio.
Professor Vidic, good luck with your technology, and thank you very much for this.
Thank you for having me.